Hello, I'm Shota Yamanaka from LY Research. In this study, we compared user behaviors of tap and swipe operations. In recent smartphone applications, there are many user interfaces where a single object can accept both taps and swipes. For example, tapping on a mail will open it, while swiping allows for its deletion. We explore how to design user interfaces that can accommodate both tapping and swiping actions. For tapping targets, there are many guidelines, such as those from the Human Factors and Ergonomics Society. However, there is a lack of design guidelines for interfaces that enable swiping. So, designing user interfaces solely based on guidelines for tapping might decrease the usability of swipes. For example, a target size of 7.2 mm is sufficient for accurate tapping, but it remains unclear how user performance with swiping might vary depending on the swiping directions and target size. To answer this question, we conducted two experiments. In experiment 1, we measured the operation time and error rate for tapping a green horizontal target and swiping it by 10 mm. We tested 5 types of operations, a simple tap and swipes in 4 directions. The target's vertical size h varied in 4 values. We repeated these tasks to collect the data from 300 trials for each participant. Regarding the operation time, we divided into 2 categories. The first is the task completion time, which is from tapping the start button to tapping or swiping the target. Naturally, swiping takes a longer time because of the additional action to move the finger. The second category is pointing time, which is from tapping the start button to the touchdown event in the target. This means that the pointing time fairly compares the time taken to contact with the screen. However, surprisingly, tapping resulted in the shortest time. And for both operation types, larger targets resulted in a quicker operation. This finding is consistent with previous studies on tapping. Regarding operational errors, we expected that tapping would yield the lowest error rate because of its simple action. However, the rightward swipe has the smallest error rate. One possible reason is that a longer time was spent for performing the rightward swipe. Furthermore, the most common error for swiping was touching outside the target, which was also the case with tapping. To analyze swiping actions, we plot where fingers touched the target. As with previous studies, taps were typically centered on the target, with a greater variance for larger targets. Conversely, swiping started touchdown at the point opposite to the movement direction. Additionally, when the target was small, touches were near the target center. But as the target size increased, there was a tendency to start from a longer distance. The touch coordinates are affected by the swipe direction. This decreases the usefulness of tap success rate models. The reason for this is that such models assume touch coordinates to be centered on the target. But this assumption doesn't hold true. Particularly, only for downward swipes, the linear regression indicates that the touch coordinates shift upwards as the target size increases. Next is the analysis of finger trajectory for swiping actions. An interesting point is that although the required swipe distance was only 10 mm, many participants executed much longer strokes. On average, swipes were around 30 mm and sometimes over 60 mm. This indicates that the participants exerted more effort than necessary. Next, let me explain experiment 2. The only difference was that the target shape became square, which increased the task difficulty. However, the results were almost identical, so I will explain the results briefly. First is the task completion time and pointing time. Tapping was quicker than swiping, which is consistent with experiment 1. Although experiment 2 involves square targets, the trends across the 5 operation types remains the same. The error rate is also similar to experiment 1. We expected that tapping would have the lowest error rate, but the rightward swiping had the lowest. This is likely because it took the longest time for swiping. The tendencies of swipe trajectory were also similar to experiment 1. The average stroke distances were approximately 30 mm and sometimes over 60 mm. The finger was placed at a position opposite to the direction of the intended swipe. The average touch coordinates varied depending on the swipe direction. The slope of the regression line for the y coordinate was in the opposite direction only for downward swipes. For the x coordinate, the slope was in the opposite direction only for rightward swipes. Therefore, the assumption of tap success rate models, which posits that touch coordinates are at the target center, doesn't hold. As a discussion, when fairly comparing the pointing times, tap has the shortest time. Therefore, according to the speed accuracy trade-off, tap should have the highest number of errors at touchdown, but the number of such errors was the smallest for tap. This result contradicts the speed accuracy trade-off, and we found that swipe negatively affects both time and accuracy. Next, we consider factors that affect the touch coordinates. Previous studies reported that which finger is used and the operational context affect the touch coordinates. In contrast, we identified 3 new factors: the operation type, the swipe direction, and the target size. These factors have a complex influence on the touch coordinates, which would reduce the utility of performance prediction models. The third point is that the target size affects the swipe performance in all directions. This was not verified in previous studies, but in realistic applications, there is a possibility of swiping targets of various sizes in different directions. Therefore, future researchers should test these factors when conducting swipe UI experiments. Surprisingly, larger targets might result in more errors for tap actions. This was a new finding. As we see in the yellow graph, there are more errors with a 60 mm target than with 7 and 11 mm targets. The green graphs show that larger targets resulted in invoking more accidental swipes. There is a tendency to move the finger slightly when touching the target because of rapid movement, which resulted in unintended swipes. We discuss some implications and suggestions. First, researchers should implement touch move events in UI experiments. If a touch move is made when a tap is requested, it should be considered an error. Next, it is necessary to derive a model that can estimate touchdown coordinates regardless of the swipe direction. The current models for predicting tap success rates are applicable to tap-only UIs. Finally, designers should make large targets that accept both taps and swipes. This study had some limitations. For example, in experiment 1, the horizontal size of the target was fixed at 30 mm, but in the future, it would be necessary to test tapping and swiping on vertically long or circular targets as well. And this time, we tested only swipes without inertia and limited the swipe directions to 4, but actual applications implement a more diverse range of swipes. There are more limitations, and these scenarios should be tested in our future work. This is a summary of this study. Thank you for listening.